Hey, how's it going? Mr. Dent here. Today I'm going to be talking about a new topic. We're still in Chapter 2, Section 2, and today I want to talk about acceleration and velocity time graphs. The things we want to be able to do after going through this screencast, we want to be able to apply kinematic equations to calculate distance, time, or velocity under conditions of constant acceleration. We also want to be able to construct and interpret velocity time graphs. And then finally, we want to be able to determine displacement using a velocity time graph. First off, let's give a quick definition of acceleration. So acceleration is basically the rate at which an object's velocity changes over time. Now this change can come in two ways. It can be a change in direction, or it can be a change in the magnitude of the velocity. So remember, velocity is a vector. That means it has a direction and it has a magnitude. So if we're increasing the velocity or decreasing it, that would be acceleration. And if we're changing the direction, that would also be acceleration. We will focus on the changing the magnitude, so things like speeding up or slowing down. Now the unit that we use for acceleration is going to be meters per second squared. Okay, so that's important that we know how we will write those units. So it's going to be meters per second squared most of the time. Like velocity, acceleration is a vector. That means it has magnitude and direction. Now in this chapter, the way we will indicate direction, because we are doing motion in one dimension, we will have a positive or negative. Now positive generally means we are speeding up. And then negative generally means we are slowing down. Now those are sort of layman's terms, but that's okay. In other words, increasing velocity or decreasing velocity. Now, that's most of the time. Now there are going to be exceptions, and that all depends on whether velocity is positive or negative. So if velocity is positive and acceleration is positive, that means we're speeding up. And if velocity is negative and acceleration is negative, that also means we're speeding up. Now one way you can look at this is that if they have the same sign, that means we're speeding up. And then if we have opposite signs, that means we're slowing down. I kind of like to think of that as if they're working against each other, that means we're slowing down. If they're working together, we're speeding up. And so an example of that would be where if our velocity becomes negative because we are moving in the opposite direction that we originally started and we established as our positive direction, then that our velocity is going to be negative, and that would be as if we're moving in the opposite direction as our initial point. And then so if the acceleration was negative at that time, then that means we'd be speeding up. Other examples, if velocity is negative or positive and acceleration is 0, of course that would be constant velocity. That means it's not changing. If velocity is 0 and then acceleration is positive or negative, that would be speeding up from rest. And then if velocity is 0 and acceleration is 0, then we would be not moving, obviously. Okay, so earlier I said we'd be talking about graphs, so velocity time graphs. But before we do that, let's look at what we talked about in the previous section. displacement time graphs, just as a quick review. So remember, on a displacement time graph, if we have constant velocity, it means we would have a straight line slope, just like this one here. And then if we have acceleration on a displacement time graph, we're going to have a curved line. Now on a velocity time graph, things are a little bit different because we have velocity on the y-axis. In the case of constant acceleration, we're going to have a straight line slope. That's the same thing that was on a displacement time graph, except in that case it would have been constant velocity. So you kind of need to pay attention to what type of graph you're looking at when you get into interpreting graphs. Now this graph shows us a couple of examples of some things that we should be able to identify on a velocity time graph. So if we have a straight line slope, that would be constant acceleration. And then if we have a straight horizontal line, that would be constant velocity. So as time goes by, the velocity is staying the same. So like in this case at 4 seconds, we were at 8 meters per second, and then at 5 seconds we were still at 8 meters per second. So our acceleration is 0, and that means our velocity is going to be constant. Now when we have a straight line slope going down, that would be what some people would call constant deceleration. We would also call that negative acceleration. And then when the object is stopped, that's when we're at 0 velocity. Some of this is probably obvious to some of us, but it's easy to get things kind of turned around when you look at some displacement time graphs and then you're looking at velocity time graphs. So please just pay attention to what's on the axis and then just interpret a graph just like you normally would. Here's another example. Of course, we already talked about acceleration. This would be constant acceleration. Again, if it's a flat line on a velocity time graph, that means we're going at a steady speed or a steady velocity. If we have a downward slope, again, it's deceleration. Now, when we have a curved line on a velocity time graph, that means our acceleration is changing. So it's like the changing velocity is changing also. So as opposed to a constant rate of change. So we're getting faster and faster and faster, and that rate is getting faster. So I mean, I know it seems kind of redundant, but hopefully you understand what I'm trying to get at. Okay, there is another one. I don't think we need to talk about that. Okay, so as I said before, we want to be able to determine displacement using a velocity time graph, and it's pretty straightforward. Basically, you just calculate the area under the curve, or in other words, the area that's between the x-axis and the curve. So let's say we were focused on the red, the object that is being shown with this red line. We could calculate the total displacement that took place in this 10 seconds, and we just calculate the area. And so it's fairly straightforward. We're just going to find the area. So basically we can break this down into two different, actually 3 different sections. And so, we have this triangle that we could calculate the area of that, and then we have this rectangle. Whoops, my line's not very straight. This rectangle, and then we have this triangle here that we could do. And then we would just add up all of those areas. So the rectangle, since it's 3 blocks or 3 seconds worth, and then we have 8 meters per second. So For that area, I'm going to have, so 3 times 8, so the area would, 3 times 8 is going to be 24. And then this triangle, we have 4 seconds. And the area of a triangle is calculated by 1/2 the base times the height. And so I can put 1/2 times the base, which is 4, and then again the height is this 8 meters per second. So and then we're going to get 16 from that. And then we can do this other triangle, and we have our base is going to be 3. So again, we're using 1/2 times base times the height. So 1/2 times 3 times 8. And we should get 12 for that. And when we add all those together, we're going to get 52. So 52 is the area under the curve, and since we were in meters per second and we had seconds here, the second is going to cancel out, so then we're just left with meters. And so there's our displacement from a velocity time graph. Not too terribly difficult. Okay, when I made this slide, this formula was a little bit bigger, so I'm going to go ahead and rewrite that so it's a little bit clearer. So the formula for finding average acceleration is basically change in velocity over change in time. And then we can break that change in velocity into velocity final, or v sub f, minus v sub I, velocity initial. Again, that's over change in time. So that's the formula that we will be using in this section to find average acceleration. So let's do a couple of those real quick, and we can be done with this. Okay, so first example problem: what is the average acceleration of a sprinter who reaches a velocity of 10.52 meters per second from rest? And that's important that we understand what that means. Rest would be 0 meters per second, and this all occurs in 5.34 seconds. So remember, our formula is, didn't mean to do that. Remember, our formula is, get my pen on. So our formula is acceleration equals VF minus VI over change in time. So we can just plug those in. So it reaches the velocity of 10.52 meters per second, so that's going to be the velocity final. And it's important you kind of get a handle on how to read those clues to know what comes first and what comes second. And then we were from rest, so that would be velocity initial, so that would be 0 meters per second. And then this all is over 5.34 seconds. And we should get, turn the page. .97 meters per second squared. All right, let's do another one. Okay, so in this case we have a shuttle bus. It's slowing down with an average acceleration of negative 1.8 meters per second squared. How long does it take the bus to slow from 9 meters per second to a complete stop? So the 9 meters per second is going to be the velocity initial in this case. So I'm just going to plug numbers in and go from there. So acceleration, remember, is VF minus VI, change in time. So my velocity final in this case is 0 because it's coming to a complete stop. So the complete stop is the last thing. So that's the velocity final. So 0 meters per second. And we're going to subtract the velocity initial. In this case, we're saying that since this was the beginning of the story or the beginning of the situation, 9.0 meters per second. And then we don't know how much time that took, so change in time. And then we knew the acceleration in this case, so I'm going to go ahead and put that over here. Now that's a little unorthodox, but hopefully you get the gist. Meters per second squared. So basically we're just solving for t. So these two guys will exchange places. So that's going to turn into -9 meters per second divided by -1.8 meters per second squared. And you should get 5 seconds. All right, that's that. Okay, so your assignment for this is going to be worksheet 2B, average acceleration. So you have a bunch of average acceleration problems to practice, and then you have another worksheet dealing with velocity time graphs, and then when you're finished with those, you can do quiz 2B. All right, this concludes this screencast. I hope you enjoyed watching it as much as I enjoyed making it. I will see you in class.